Now it's recording.
Thank you.
Can you see this OneNote slide?
Yes, we can.
Okay, good. So this week I will start with the assumptions. The first assumption so I assume that there is a point x bar such that the gradient vanishes. We have a cost function, and the second assumption is either f is convex, but I make a little bit more. So I assume that the second derivative is positive definite. So last year we recognized that then x hat is a minimum point, local minimum point, and if f is convex, it's even a global minimum point. The general strategy for finding the minimum point, is okay. So assume that we have found an approximation. And we want to compute next the better one. So for example, we have some criteria that we have at the moment. We have a knowledge that gradient of f at the point xk, the norm, whatever norm, so the length of this vector is not 0. So we have some threshold value which is, of course, positive. And we want to find a point in such a way that the threshold value or the length of this gradient is less than this threshold value. This is our criteria. Next step is to find a search direction. It is some vector in Rn. So we start from this point xk and we go into this direction where the function values decreases. Sorry, here? No, S like a search direction. And then a new approximation. Xk plus 1 is xk plus some matrix ak times the search direction xk. And at every step, we have to find this. What is this AK? So it's a square matrix. And then, of course, we have to check whether the new approximation is satisfying the condition. So the norm and if the norm of the new approximation is less than epsilon threshold, stop. Oops. Else return to step. What was the step? Okay, let's change this one. So this is step 1. Step 2. So step 2. And you carry out this iterative process until you have achieved this criteria. So we have to update at every step the search direction, and then we have to update this matrix AK. And these are the, let's say, the general strategy, how all the iterative techniques work. So whatever algorithm you will find, they follow this one. So you start from point, you took the search direction, then you have this matrix AK. What is the matrix? So this makes the distinction between the various algorithms. And then you compute the new approximation. You have the optimality check, so that the gradient of the function at the new point is small enough, close enough to 0. Then you stop. Or of course you can make there are more refined criteria, like the change from the previous approximation is small enough. So the difference between two consecutive points is small enough. Then you make an assumption that, okay, we are close enough to true minimum. Oops. So the idea is quite simple. So I have here equicontour line. Or actually surfaces. So the lines where the function gets the constant values. So for example, if we have for example, a quadratic function, the equicontour lines in 2D, they are ellipsoids. Like this. So here at every and I assume that here somewhere is x hat. It's the minimum point. And then I have here somewhere xk. And I take the search direction. And of course, in the very beginning, the obvious search direction is minus of the gradient. So this is, for example, this is because in this direction, the function O but then in which, for example, in the gradient method, you go just along this line. So, okay, let's forget. So at least here is some, we go into that direction. So we compute. Oh. So we take just 1D minimization. We go along the search direction and we minimize with respect to t, which is some positive number. And here we get, for example, somewhere here is then our point. Xk plus 1. Because from this 1D minimization, we get step length tk, which is something positive. This is the idea of the gradient method. So in the very beginning, in this gradient method, we have to, so let's put some space here. So the search direction is always minus of the gradient of the function at the point. So at every point, we have to compute the gradient. Then you have to perform with respect to the t variable. Of course, in practice, you are not able to do it exactly, but I will take some examples where you can do it exactly. And there you get tk. And then the new approximation xk plus 1 equals xk plus tk times sk, or it's the same as xk minus tk times gradient of if at xk. So this is the simplest way of doing. So how we do the minimization? 1D minimization. Sorry. But it's complicated. Okay. So Okay. What can you see now? Can you see the slides?
Yes, we can.
So first, what are the 1D minimization algorithms which we can use? The first one is, of course, from the freshman calculus Newton method. Because we have to compute the step length also in some. There is a second iteration inside this big iteration. Or you can use some derivative-free techniques like quadratic interpolation method or bisection. Golden section shirts, Fibonacci shirts, or whatever. So the first one, the Newton method, is quite simple. So we compute at every step. Now my function f is not the same as the cost function on the previous slides. So now f is a function of one variable. Maybe I should change it for function depending on t. So we exploit, but you can't see this one. This is strange. So I have to make like this. But can now the people who are remotely watching can you see the slides now?
Yes, we can.
Good. So now we have the case that when we have this twice differentiable function of one variable, so we exploit the quadratic approximation of the function. So once again, the Taylor formula. We compute f tilde is the approximation, quadratic approximation at the point xk, and we compute the approximation being the minimum of the f tilde. And we compute the derivative of f tilde and require that it vanishes at some point. And the point is xk plus 1. And when you compute the derivative of the second order polynomial, you get first order polynomial. The constant I had here. Okay. When we compute the derivative, the constant here vanishes. So here is the first order polynomial the derivative of f at xk times x minus xk. The derivative of this one is the constant here, f prime. And then you compute the derivative of the second order polynomial. It is the once again the second derivative of f at the point xk times xk plus 1 minus xk. And xk plus 1 is the point where the derivative must vanish. And when you solve this equation, you got the iteration. So xk plus 1 equals xk minus f prime divided by f2 prime. So the derivative is divided by the second derivative at the point xk. And this algorithm works very well. Of course, the problems with this one is that computing the derivative, if this function f is this function which is defined on the line, so the computation of the derivatives might be quite difficult. First order and second order derivative. But if you can compute it, this is very fast. It finds very fast the step length in the 1D minimization. Then so there is some results concerning the convergence rates. It says that if certain criteria are satisfied.
Excuse me, did you change the slides?
Yes.
We cannot see anything. The new slides.
You cannot see anything from the slides.
New slides, no, we cannot. The old ones, we can.
Okay, there is some. So it. Can you see it now?
We can, but I think it's the last slide.
It's the Newton method.
Yeah, it's the Newton method, and it says assumption fx is at least twice.
Can you see the new convergence of the Newton method?
Yeah, we can see it.
Okay. So if the function is f is twice continuously differentiable, so the second order derivative exists and it is continuous at some interval where we know that there is this minimum point. And the minimum point satisfies the condition that the second derivative is non-zero, it's non-vanishing. Then the condition here is quite complicated. But it says that if you choose the initial point for the Newton method close enough the true minimum point, then these two conditions here for sure is satisfied. So, and then the algorithm converges, and even it will converge quadratic rate, meaning that at every step, the number of correct decimals or digits doubles. So if you have in approximation, you have 4 correct digits, in the next one, there is 8 correct digits. So it's very fast algorithm. And actually it was known already by the, for example, in the hieroglyphs in cuneiforms, you can find this method applied for computing the square root of a number. So it was well known even in ancient times. So for example, here I have an example of function fx equals e to the power minus x minus cosinus x. And on the interval 0 to pi over 2, there is a minimum point. Because if you take, okay, maybe it's better to look at the derivative. So if you compute the derivative, it is minus e to the power minus x plus sinus x. And if we put there x equals to 0, the derivative is negative. And if you put x equal to pi over 2, sinus is 1, but minus e to the power minus p over 2 is less than 1. So the derivative is positive. So because the derivative function is continuous, on the ends of the interval, at the other end it is negative and at the end positive, there must be a 0 point somewhere. So there is at least one point where the derivative vanishes. Of course, at this point, we don't know if it is minimum point or maximum point or a saddle point. But then for that, we compute the second derivative. It's e to the power minus x plus cosinus x. And if e to the power minus x is always positive, and cosinus x is also non-negative on the interval from 0 to pi over 2. It vanishes, cosinus x is 0 only at the other end. So the second derivative is always positive, saying that this function is convex on that interval. Sorry? The function is convex on the convex interval from 0 to pi over 2. So it has one point where the derivative vanishes. It is a convex function because the second derivative is positive. And then it means there is exactly one minimum point on that interval, inside the interval from 0 to pi over 2. Pi over 2. So on that interval. So then we just start the iterations. I take any point on that interval, so I have started from 0. I compute using this iteration. Here is 0 minus 0 minus 1. So, and 1 plus 1. So it is 1/2. Then I substitute this x1 on the left-hand side, and I compute x2. So here you see already that there is 0, 5, 8, 5, 6, 4, 3, 8, 1, 7. And because in x1 and x2, the first digit is same, then I make a wild guess that here is already the first two is correct. So 5 and 8 are correct digits. Then I substitute x2 on the right hand side of my iteration and compute x3. And it provides 5885 29413. And because here I can see that in x3 and x2, first two digits are the same. Based on my knowledge on the how the Newton method works, I make the guess that these 4 digits in x3 are correct. Yes. Sorry. Now I don't really understand. It's not a what complex. But do you mean inflection points, a point like going like this? No, because this is positive. It means it must be like this all the time. And then if you take, and then when you compute x4, you see that here are 4 digits the same. So I make the guess that here already 8 digits are correct. And when I compute x5, and if I would compute all the 16 digits, you would notice that here already the 9 digits are the same. So x5 is correct in 16 decimal places. So this Newton method, when it finds the minimum, if it is applicable, it finds it's very fast. But of course, yes. Yes. So why I choose this one? So this is always, if you look, for example, MATLAB works like this, that you take this function here and maybe you can compute the derivative because you want to compute the point where the derivative goes to 0. You just make a guess. So you choose first the interval where the derivative at the other end is negative and the other end it's positive. Then you know from this, I can't remember now. It is always the same, guys. Bolzano, Weierstrass, which says that on this interval, there must be a 0 point of a continuous function. But this one does not work if we have the second derivative goes to 0 at the minimum point. So for example, you can take, for example, the function x to the power 4. The second derivative, the minimum point is 0. And the second derivative is also 0. And the derivative is 0. So it means that you have here, when xk is not 0, but close to 0, you have the difficult task that you are dividing with something which is very close to 0, something which is also close to 0, but is bigger one. So it might that this Newton method, okay, maybe it works, but it converges very, very slow. And then, of course, there is the problem that if you choose this x0, so the interval where you start these iterations, if this is too big, then there is the problem that, so it is called slow death. The iterations, it can take 100,000 iterations, and it slowly approaches the minimum point. And then at the very end, when it is close enough, in 1 or 2 steps, it finds the very good approximation. So the essential part in the Newton method is how to find very good initial guess. And there you have to do this bisection, searching methods. So golden section search or Fibonacci search or whatever. So it's available when you know that the function is twice differentiable. So when it is smooth enough, then it is for sure very good. But then if you don't have any knowledge about the smoothness of the function, then you should choose something else. The quadratic fit line search is based on Newton method as well. But we don't compute the derivative of the function itself. We take 3 known points. We just choose 3 points from real line. And we make a quadratic interpolation. So you take a quadratic interpolation of the function f, so that at the point x0, the polynomial of p gets the value f at x0. At x1, it gets the value f at x1, and x2, it gets the value of f at x2. And I use here, you can compute the interpolation polynomial in every way, but I have used the divided differences because it is the simple, at least to me, it is the simplest one. So a0 must be the value of the function at x0. The constant a1 is the first divided difference between the function at x0 and x1. So this one is actually the approximation of the first derivative at point x0. And then the constant a2 is the second order divided difference of the function between the with respect to the points x0, x1, and x2, and it is somehow an approximation of the second derivative of the function f. And this can be computed even if we don't know anything about the smoothness of the function f. So we force the function to become smooth. And then, because it is the second order polynomial, you can compute the minimum point or the derivative of this function. Of course, all the time we have to check whether this constant a2 is positive or not. Because if a2 is negative, it is a concave function, and we are trying to find the maximum point. And if we are if a2 is a positive value, then we compute the minimum point of this one. And it is the new point in our set. So the derivative of our interpolation polynomial at x star must be 0. You can compute this x star, and then you have to compute 4 function values. What is the value of function at x0, x1, x2, and the new point x star? And you remove from the set the one with largest value. So of course we hope that x star is the new point and one of the 3 previous points will disappear. And then you continue. You find a new quadratic interpolation with the 3 remaining points. And then you compute your new approximation. So this is, in a way, this is a derivative-free technique. We don't have to worry about the derivatives of the function f or the second order derivatives of the function f. We have to know only that the function f itself is continuous. Everything else is done by this interpolation. So we, in a way, we force this function to behave like a smooth function. Then we have the golden ratio search. So the golden ratio here is the number tau. I can't remember. It's the root of the second order function. So I have, once again, I have an interval from A to B. And then I choose 2 points, x1 and x2. And I compute the values of the function at x1 and x2. And if x1 is bigger than x2, then I make the assumption that the minimum point is between x1 and b. And if this value fx2 is bigger than fx1, then it's between a and x2, the minimum point. So I'm minimizing the length of the uncertainty where the minimum point will be. So this is the, and I choose the numbers x1 so that it is a times tau minus 1 plus b times 2 minus tau. And x2 is a times 2 minus tau plus b times tau minus 1. So those are the points. They are, I guess they are symmetric on the interval. So the length, the point tau is defined in a way, was it like this, that you have the interval, the length of the smaller interval to the bigger interval is the same as the bigger interval, the ratio between the bigger interval and the whole interval. So this is the golden section of the interval, and you take it from the both sides. So it must be symmetric, two symmetric points. And then you just make this comparison. You compute the function values at x1 and x2. And if the value at x1 is bigger than x2, then choose a equals x1 and b equals b. And otherwise you take a equals a and b equals x2, and then you repeat. And for sure, the interval will all the time, the interval will diminish. It's smaller and smaller. And this is the technique which, for example, MATLAB uses when it minimizes. There is this function fmin in MATLAB. So in the very beginning, if you choose the options, you can see that there is this golden section rule. And then it jumps to the Newton method. So you easily can, that after n function evaluation, the minimum point is within the interval of length, which is b minus a times tau minus 1 to the power n. So with this one, you can control how small the final interval will be. So let's return back. So I assume that you have already studied these things in the freshman calculus. So the Newton method, various bisection methods. So bisection methods, they are these Fibonacci search, golden section search, and so on. So I assume that the cost function is sufficiently smooth, and mainly I will consider convex functions. And we want to find this optimal of the minimum point of the cost function f. And if we have a convex smooth function, the optimality criteria equals, so the gradient must vanish at the minimum point. And of course, if we have this convex function, I made the assumption in the very beginning, I assume that the second derivative or the Hessian matrix at every point is positive definite, or at least positive semi-definite. Here is once again the general strategy. So we have the search direction. On my slides, the search direction is D. We perform the 1D minimization. Not always. So I will present on Wednesday a couple of algorithms which don't use this 1D minimization, or the 1D minimization is hidden in the algorithm. We don't notice that there is 1D minimization. There we get, okay, there we get the step length, D0. We compute the new approximation, X plus D0 times D, step length plus the search direction. And then we update the search direction and we stop when the gradient, the norm of the gradient is small enough. And it doesn't matter which norm you choose. Is it the maximum norm, Euclidean norm? So the you take the sum of squares of the coordinates, or if you take the sum of absolute value of the coordinates, so IL1 norm, it doesn't matter which norm you use. Because anyway, we more or less we obtain the same point. So once again, the gradient method starts with the minimizing fx. F is now the cost function in Rn, real valued function, smooth. We have found at some point the approximate solution xk. Search direction is the minus of the gradient. And then we define a function of one variable, phi of alpha. Alpha is now the step length. We perform the 1D minimization. We get the step length. And the new approximation is xk plus alpha k times sk, where sk is the minus of the gradient. So here is once again the picture. I have taken, now my example is not this is the one of the Rosenbrock functions. So it is function of two variables. It is fourth order polynomial in x variable, and in y variable it is second order. So altogether it is fourth order cost function. And you can see from the if it is not too small, so you can see that this function vanishes from x1 equals 1 and y equals 1. So at the point 1, 1, somewhere here is the minimum point. And here we compute, we have xk here, we compute the gradient, and we make the 1D minimization. So here you cannot see the prime here. It's for some reason this gradient vanishes when I make the EPS figure of the MATLAB figure. So the nabla operator disappears here. And then here is the new, and then you have here the equicontour line, and of course always the gradient is orthogonal. It's the normal to the equicontour line at the point. So here is the, let's say, more or less the difficulty with the gradient method. All the consecutive search directions are orthogonal to each other. And it's a bit of a problem for the gradient method that at some point it can be that, for example, if these equicontour lines which describe the function very well, if they are very small, let's say length very long in one direction and very small in one direction, then the gradient method starts to make this zigzag movement. So it doesn't find very fast the minimum point. It converges very slowly. So for example, yes? So here are, if I understood your question correctly, here is an equicontour line. So on this curve, the function values are exactly the same as the function value at xk. Then here in this inner curve, the function values are smaller, but they are constant. And then of course, if you have in 3D, then they are surfaces. And if you have 100-dimensional space, then they are also surfaces or hypersurfaces in this 100-dimensional space. It's constant. So here is a simple quadratic function. And we use the gradient method. So we compute the gradient. The gradient vanishes at 0. So we know here that the 0 is the minimum point. We can compute also, if we compute the second derivative or the Hessian matrix. The Hessian matrix is nothing else than the matrix which has the same elements as in the gradient here. So 16 on the first diagonal, then on the second diagonal, and 4s on the off diagonals. So the matrix is clearly positive definite. So we have here a convex optimization problem. So we don't have to worry. When we find the minimum point or the 0 point of the gradient, then it's already the minimum point. Let us pretend that I'm stupid. I don't understand that the gradient vanishes at 0. I make a guess that my initial guess is with coordinates -1 and 2. So the point on the coordinate system -1, 2. I compute the search direction, so minus gradient of f at x0. So here is -16 plus 8. So it's -8, but multiplied by -1, it is 8. 4 times -1 is -4, plus 10 times 2, it's 16. So it's -16 here. Okay. Here is my search direction. I may perform the 1D minimization. But because my 1D minimization problem, I can compute now everything analytically exactly. So I compute the derivative of this function 5 and with respect to alpha, so the alpha variable. So it means that the derivative of phi over alpha is the gradient of the function f at the point x0 plus alpha times s0. So the derivative of the outer function, which is the function f, multiplied by the derivative of the inner function, which is the derivative with respect to alpha, which is nothing else but the vector s0. But now we have to remember that there are the outer derivative is a vector and the inner derivative is also a vector. Then it's a scalar product. And this scalar product must vanish. Okay, I have computed S0. I have to compute the gradient of f at x0 plus alpha times S0. So I put here x0 plus alpha times S0. Okay, maybe I have dropped. Yes, I have dropped this 8. And my new search direction is only the point 1 minus 2, because the search direction, it doesn't matter if I divide it by a positive constant. So the gradient of x0 plus alpha times S0 is here, 8 times -1 plus alpha and 16 times -1 minus alpha. And I take the scalar product with S0, which is 1 minus 2. The result is -40 plus 40 times alpha, and it must be 0. So this one goes to 0 when alpha equals 1. It means that -1 plus S0 is the new approximation. And it gives directly the point with 0 coordinates. And then you check the optimality. Okay, the gradient vanishes at x point, at x1. You compute the Hessian matrix, it's positive definite. Conclusion, x1 is the minimum point. If we have a quadratic functional, so we have a 1/2 times quadratic form, so x transpose times ax. minus scalar product of the b times x. So the gradient equals here is ax minus b, as in our previous example, where A was just 2 by 2 matrix. In our previous example, B was equal to 0. So the minimization of the quadratic functional is nothing else than solving the linear system of equations. I compute the search direction minus gradient of f at xk. It's b minus a times xk. I compute the 1D minimization problem. For that one, I have to compute this phi over alpha. So I substitute this function, the vector xk plus alpha times sk. Here it's alpha squared divided by 2. And then you have this number, quadratic form of the matrix A with respect to xk, the search direction sk, alpha times the gradient of our cost function at the point xk, and sk, which is my b minus, it's minus of the gradient. And then we have here the value of the function at the point xk. And then you compute the derivative of the function phi with respect to alpha. So, and you try to find the step length alpha k in such a way that the derivative vanishes. So here comes the derivative of alpha squared is 2 times alpha and divided by 2. So it's alpha k with this number minus here is alpha, the derivative of alpha is 1, and then I multiplied minus, so it's minus b minus alpha xk, scalar product with sk, but this vector is the same as sk. So alpha k equals the norm of the search direction squared divided by this one. And then you can compute for quadratic functional, you can compute this alpha k exactly. So the 1D minimization can be computed exactly if you can compute the gradient of the function f at xk exactly. And then you have the new approximation. The basic property of gradient method is that the consecutive search directions are always orthogonal to each other. And this is, and some cases we obtain this zigzag phenomenon, which says that it converges very slowly towards the true minimum. Okay, this one, this Armijo inexact line search I will take on Wednesday morning. And on Wednesday morning, it is once again in a different lecture room. It is, was it L4? Have you the same information? DS101. Yes. And it's once again a completely different lecture room. And there is once again the problem that how I can get my setup correctly. Yes, DS101. It's in the Tietotalo, just behind the restaurant, if I'm correct. Okay, see you on Wednesday morning.